Imagine a world alive with invisible signals, where devices communicate by whispering through the air instead of relying on the tangled mess of wires that once cluttered our desks and pockets. This world exists thanks to wireless technology, and among its most familiar names is Bluetooth. To understand how Bluetooth came to be, it helps to journey back to the origins of wireless communication, a story that spans centuries, driven by human curiosity and ingenuity. The roots of wireless technology reach deep into the scientific discoveries of the 18th and 19th centuries. Long before anyone imagined connecting a phone to a headset without a cord, scientists were unraveling the mysteries of electricity and magnetism. In the early 1800s, Hans Christian Ørsted and Michael Faraday made pivotal discoveries showing that electricity and magnetism were intertwined. Their work paved the way for James Clerk Maxwell, who, in the 1860s, formulated equations describing how electromagnetic waves traveled through space. Maxwell's equations did not remain theoretical. In the late 19th century, Heinrich Hertz provided experimental proof that these waves could be generated and detected, demonstrating that invisible energy could leap across space. The practical applications of these discoveries soon became clear. In the 1890s, Guglielmo Marconi harnessed electromagnetic waves to send messages wirelessly across the English Channel, creating the first wireless telegraphy system. Shortly after, Reginald Fessenden achieved the first wireless transmission of a human voice. These breakthroughs seemed miraculous at the time, unlocking the possibility that information could travel vast distances without physical wires. The air around us, once thought empty, was suddenly filled with potential. Fast forward to the late 20th century, and wireless communication had become routine. Yet, new challenges emerged. Personal computers, mobile phones, and a growing array of electronic gadgets were proliferating in homes and offices. Each device needed to connect to others: printers, keyboards, headphones, but the connections were messy. Cables snaked across desks, creating clutter and limiting mobility. It was clear that a new solution was needed, one that would allow devices to connect seamlessly and wirelessly over short distances. This was the environment in which Bluetooth was born. The story begins in 1989 at the Swedish telecommunications company Ericsson. Engineers there, notably Dr. Job Hartson and Sven Mattisson, set out to develop a technology that could eliminate the need for short-range cables. Their goal was simple yet ambitious: make it possible for devices to exchange data without physical connections, using radio waves instead. The principal design work began in 1994, and the technology they created would eventually become known as Bluetooth. Bluetooth operates using ultra-high frequency, or UHF, radio waves in the 2.4 GHz band. This particular slice of the electromagnetic spectrum is known as the industrial, scientific, and medical, or ISM band, a range of frequencies internationally reserved for unlicensed use. The choice of the 2.4 GHz band was strategic. Devices worldwide could use it without running afoul of local regulations, and it offered the right balance of range and power consumption for the short-range communications envisioned by Bluetooth's inventors. However, the airwaves are crowded. Wi-Fi, microwave ovens, cordless phones, and even baby monitors all compete for space in the 2.4 GHz band. To ensure Bluetooth signals could travel undisturbed, the technology employs a clever technique known as frequency hopping. Instead of broadcasting on a single frequency, Bluetooth devices rapidly switch, or hop, between 79 different frequencies, all centered around 2.45 GHz. This process happens hundreds of times every second. The result is a communication link that is both robust and resistant to interference. If one frequency is momentarily blocked, the devices simply hop to another, keeping the conversation going without interruption. From the outset, Bluetooth was designed to be low power. Early versions of the technology allowed devices to connect reliably within a range of about 10 meters, roughly 33 feet, without draining their batteries. This made Bluetooth especially well-suited for portable gadgets like wireless headsets and mobile phones, which needed to communicate while preserving precious battery life. Bluetooth's modest range was a deliberate choice. It was never intended to replace long-distance technologies like Wi-Fi, but rather to quietly eliminate the need for cables in personal spaces. Yet, as with any promising technology, success depended on more than technical achievement. If every company created its own version of wireless connectivity, the market would be flooded with incompatible devices, each speaking a different language, unable to communicate. Recognizing this, a coalition of technology giants came together in 1998 to form the Bluetooth Special Interest Group, or SIG. Ericsson was joined by IBM, Intel, Nokia, and Toshiba in an effort to standardize the technology. Their goal was to ensure that any Bluetooth-enabled device, regardless of manufacturer, could connect seamlessly with others. The name Bluetooth itself has an interesting origin. In 1996, as the industry group was taking shape, there was still no official name for the technology. Jim Cardack of Intel proposed Bluetooth, inspired by Harald Bluetooth Gormson, a 10th-century Scandinavian king known for uniting Denmark and Norway. The analogy was fitting. Just as King Harold had brought together warring tribes, the new wireless standard aimed to unite disparate devices under a single protocol. The name was originally intended as a placeholder, with plans to choose something more conventional later. But as alternative names ran into legal obstacles, Bluetooth persisted and eventually became the permanent brand. The logo, for those with a keen eye for history, cleverly combines the runic initials of King Harold's name, a subtle nod to the technology's roots. The first consumer device to use Bluetooth, a hands-free headset, was launched in 1999. Not long after, the Ericsson T36 became the first Bluetooth-enabled phone, though it reached consumers in 2001 as the T39. From this point on, Bluetooth began appearing in a growing array of products, from wireless mice and keyboards to speakers and smartwatches. By 2020, approximately 4 billion Bluetooth devices had shipped worldwide, a testament to the standard's broad appeal and practicality. At its core, Bluetooth is a standardized protocol for exchanging data wirelessly over short distances. It was designed to replace legacy cable standards like the RS-232 serial interface, offering a low-cost, low-power alternative that could be embedded in a wide range of consumer products and electronics. Devices equipped with Bluetooth use built-in antennas to send and receive signals, with most operating in what is known as Class 2 mode, providing a typical range of about 10 meters. For special applications, there are also Class 1 devices, which can communicate over distances up to 100 meters, and Class 3 devices, with a much shorter range of just 1 meter. When two Bluetooth devices want to communicate, they go through a process known as pairing. This is a digital handshake, during which the devices exchange unique identification information and, often, security keys. In many cases, users are prompted to enter a PIN code to complete the pairing, adding a layer of security to prevent unauthorized connections. Once paired, devices can automatically recognize and reconnect to each other in the future, making subsequent use effortless. Bluetooth's technical sophistication extends to how it manages device discovery. When a user activates Bluetooth on their phone or laptop, the device enters a discoverable mode, sending out radio signals to announce its presence. Other Bluetooth-enabled devices nearby can detect this signal, display the device name, and initiate the pairing process. This system is designed to be simple for users, yet robust enough to handle the complexities of wireless communication in environments crowded with signals. Over time, Bluetooth has evolved to meet new needs. The original version, often called Bluetooth Classic, was optimized for steady, persistent streams of data ideal for audio streaming between a phone and wireless headphones, for example. As the number of connected devices in homes and workplaces grew, the demand for even lower power consumption led to the development of Bluetooth Low Energy, or BLE. This variant, now central to the Internet of Things ecosystem, is designed for devices that need to send small bursts of data intermittently, such as fitness trackers or smart home sensors, while using as little energy as possible. Despite its ubiquity, Bluetooth does have limitations. Its range is intentionally short, and its data rates are lower than those of Wi-Fi, which is designed for high-speed connections over longer distances. Bluetooth's focus has always been on convenience, simplicity, and interoperability within personal spaces. It is the quiet enabler behind the seamless connection of headphones, speakers, keyboards, watches, and an ever-expanding universe of smart devices. The governance of Bluetooth remains in the hands of the Bluetooth SIG, now a consortium of more than 35,000 member companies. The standard has seen numerous updates, but its core mission endures: to unite devices, free people from the tyranny of cables, and make wireless connectivity as simple and reliable as possible. While the IEEE once standardized Bluetooth as 802.15.1, it no longer maintains this standard, leaving the ongoing evolution of the protocol to the SIG. Looking back, the birth of Bluetooth is a story woven from the threads of scientific discovery, engineering ingenuity, and industry collaboration. From Maxwell's elegant equations and Hertz's spark-gap transmitters to the hands-free headsets and smart gadgets of today, each chapter in this history has brought us closer to a world where information flows effortlessly through the air. Bluetooth's origins may be rooted in the distant past, but its impact continues to shape the way we connect, communicate, and imagine the future. Imagine the moment when a pair of wireless earbuds springs to life, seamlessly connecting to a nearby phone. There is no visible tether, no need for a central router, just an invisible handshake playing out in the airwaves above our heads. What makes this effortless pairing possible is a highly orchestrated system of protocols, profiles, and mechanisms, Bluetooth's internal architecture, a hidden world pulsing within billions of devices. To truly appreciate how Bluetooth has become the connective tissue of so many technologies, we must step inside its signal and explore how its architecture and protocols knit the digital world together. At its core, Bluetooth is a radio technology, but not just any radio. It operates in the 2.400 to 2.4835 GHz band, a part of the spectrum internationally set aside for unlicensed use by industrial, scientific, and medical devices. Within this crowded slice of the spectrum, Bluetooth stands out for its ability to communicate directly between devices, no router or access point required. But with baby monitors, cordless phones, and Wi-Fi networks all competing for space, Bluetooth faces a challenge: how to keep its message clear amid the cacophony. The answer lies in a technique known as frequency hopping spread spectrum, or FHSS. Instead of transmitting on a single frequency, Bluetooth devices rapidly jump between channels within the ISM band, sometimes hundreds of times a second. This hopping serves a dual purpose. It reduces the likelihood of interference from other signals and makes Bluetooth inherently resilient in noisy environments. Frequency hopping is just the beginning. The Bluetooth ecosystem is not monolithic. It consists of two primary radio systems: Classic Bluetooth, also known as Basic Rate/Enhanced Data Rate (BR/EDR), and Bluetooth Low Energy, or BLE. Classic Bluetooth uses 79 channels within the ISM band, primarily for audio streaming and bulk data transfer. Its design emphasizes steady point-to-point connections, making it ideal for use cases like wireless speakers or file transfers between laptops and phones. Bluetooth BLE, in contrast, divides the spectrum into 40 channels and is optimized for low-power operation. Its data rates and power consumption are tailored for battery-sensitive devices like fitness trackers, sensors, and beacons. Also introduces diverse communication topologies, not only supporting classic point-to-point links, but also enabling broadcast modes and even mesh networks where thousands of devices can relay messages cooperatively across an entire building or campus. At the physical layer, the foundation of the Bluetooth protocol stack, these two systems share the ISM band but differ in their modulation schemes and channel arrangements. Bluetooth BLE, for example, uses Gaussian frequency shift keying, GFSK, modulation and specifies a mandatory data rate of 1 megabit per second, with optional lower or higher rates available for specialized scenarios. Channel hopping is not random, it is adaptive. Devices using adaptive frequency hopping can monitor the spectrum, identify channels with high interference, and dynamically avoid them. This agility helps Bluetooth coexist with other technologies, making the best use of available bandwidth and reducing the risk of dropped connections or garbled data. As we move up the protocol stack, Bluetooth's architecture reveals itself as a carefully layered system. Communication is managed between two main components, the controller and the host. The controller is the physical and logical part responsible for radio communication, channel hopping, and low-level link management. It encompasses the physical (PHY) layer, the link layer, and the host controller interface (HCI), a pivotal boundary where higher-level software on a device's operating system can command and control the radio hardware. The host, in turn, houses the higher layers, logical protocols, services, and profiles that give Bluetooth its flexibility and power. Within this architecture, a suite of core protocols orchestrates how devices discover each other, establish connections, exchange data, and manage services. The baseband protocol controls how devices find, synchronize with, and communicate over the air. The Link Manager Protocol, LMP, negotiates the parameters of the connection itself, covering security modes, encryption, and power-saving features. Above these sits the Logical Link Control and Adaptation Protocol, L2C AP, which acts as a traffic manager, multiplexing multiple logical data streams over a single connection and providing segmentation, reassembly, and quality of service features. For applications that require serial data streams, such as emulating a cable link, Bluetooth provides the RFCOMM protocol, which mimics the venerable RS-232 serial port. Telephony applications may use protocols like TCS binary or AT commands, while adopted protocols such as PPP, UDP, UDP, TCP/IP, and WAP allow Bluetooth to transport internet and web traffic when needed. Device discovery. The process by which one Bluetooth device finds another nearby is a fundamental procedure, yet it differs across Bluetooth versions. For classic Bluetooth, discovery is an active process. A device sends out inquiry packets, probing the ether for nearby devices willing to respond. Bluetooth BLE, by contrast, often uses passive scanning, where a device listens on 3 designated advertisement channels, waiting for other devices to broadcast their presence. This difference is not merely academic, it reflects the power-saving priorities of BLE devices and the flexibility required for diverse applications. Discovery is the first step in building a Bluetooth connection, and the tools for it are integrated into nearly every operating system and mobile platform today. Once 2 devices have found each other and agreed to communicate, their interaction is shaped by what Bluetooth calls profiles. A profile is, in essence, a recipe for a particular type of communication, defining what data is exchanged, what actions are supported, and how devices should respond to each other. There are profiles for everything from hands-free phone calls to heart rate monitoring, from file transfers to wireless keyboards. In Bluetooth BLE, the dominant paradigm is the Generic Attribute Profile, or GATT. GATT organizes data as a hierarchy of services, characteristics, and descriptors, each uniquely identified by a universally unique identifier, or UUID. For example, a heart rate monitor might expose a service with characteristics representing the current heart rate, sensor location, and battery level. This model allows for great flexibility, as new services can be defined and registered without altering the underlying Bluetooth protocol. The robustness and versatility of Bluetooth would mean little, however, without a strong foundation of security. Over the years, Bluetooth security mechanisms have evolved in response to new threats and use cases. At the most basic level, Bluetooth offers multiple security modes. Mode 1 is non-secure, with no authentication or encryption. Mode 2 provides service-level security, granting or denying access to specific services, and Mode 3 enforces link-level security, requiring devices to authenticate and encrypt all traffic before a connection is established. The underpinning of Bluetooth security is a system of keys and cryptography. During pairing, devices exchange information and generate a shared secret link key, often derived from PIN codes and strengthened by cryptographic algorithms. This link key forms the basis for authentication, a challenge-response process that verifies each device's identity, and for encryption, which scrambles the data so that unauthorized listeners cannot decipher it. In classic Bluetooth, the E0 stream cipher is used for encryption, with keys generated from device addresses, random numbers, and the shared link key. With each new version of Bluetooth, the security landscape has shifted. Early implementations relied on legacy pairing schemes, but later iterations introduced secure simple pairing and secure connections, leveraging stronger algorithms such as Advanced Encryption Standard Counter with cipher block, chaining message, authentication code, hash-based message authentication code, secure hash algorithm 256, and elliptic curve Diffie-Hellman for key exchange. The security framework relies on 4 main ingredients: the device's unique address, 2 secret keys, and a random number generated for each session. Key sizes and algorithms are now configurable, enabling devices to balance compatibility and security according to their needs. The importance of security is underscored by practical advice. To minimize risk, users are encouraged to authenticate and authorize devices, use pairing codes, switch off Bluetooth when not in use, and unpair devices from shared or public environments such as rental cars. Even with these defenses, Bluetooth is not immune to security threats. Unauthorized interception and access remain concerns, especially for older devices or those using legacy protocols. The Bluetooth Special Interest Group has responded by enhancing security features in newer versions and by providing guidelines for safer device management. Still, the onus remains partly on users to stay vigilant. Turning off discovery mode and unpairing old or unused devices can go a long way toward keeping personal data safe. Bluetooth's evolution has been marked not just by changes in security, but also by dramatic leaps in speed, range, and versatility. The journey from version 1.0 to 6.0 has been a story of constant refinement. Each upgrade brings a new set of capabilities, often tailored to the emerging needs of the digital landscape. The first version offered a modest 1 megabit per second data rate and a typical range of 10 meters. With version 2.0 and enhanced data rate, speeds jumped to 3 megabits per second. Version 3.0 introduced the option to piggyback on 802.11 Wi-Fi links, briefly pushing rates as high as 24 megabits per second for specialized use cases. but it was version 4.0 that marked a turning point, ushering in Bluetooth Low Energy. BLE offered a range of about 33 feet, vastly improved battery life, and the ability to connect peripherals, sensors, and beacons with minimal energy cost. The subsequent arrival of Bluetooth 5.0 doubled data rates and quadrupled range, targeting the burgeoning Internet of Things. Version 5.1 added precise location and direction finding features, while 5.2 introduced BLE audio, enabling more efficient, higher quality sound transmission. The most recent update, 5.3, further improved efficiency, reliability, and security, reflecting the relentless pace of technical innovation. Bluetooth BLE in particular has opened up new possibilities. Its low-power operation, broad compatibility, and simple pairing process make it attractive for a vast ecosystem of devices, everything from smartwatches to asset trackers. BLE's mesh networking capabilities allow for the creation of expansive device networks, such as connected lighting systems and smart buildings. These mesh networks come with their own challenges, especially in terms of complexity and scalability, but they represent a major step forward in what Bluetooth can achieve. Meanwhile, the concept of cloud connectivity for Bluetooth devices is gaining traction, with new solutions emerging to bypass traditional one-to-one pairing in favor of broader, more flexible access. New features continue to emerge at the cutting edge. Bluetooth channel sounding, for example, is a secure, fine-ranging technology designed for precision location tracking in industrial and commercial settings, an innovation with the potential to transform logistics, security, and asset management. Auracast broadcast audio promises to revolutionize shared listening experiences in public venues, allowing groups of people to connect to the same audio stream simultaneously. These developments hint at a future where Bluetooth is not just a tool for personal gadgets, but an essential part of our connected environment. Yet, for all its sophistication, Bluetooth remains accessible and cost-effective, a testament to the careful balance struck by its architects. Its limitations are real. For instance, Bluetooth BLE's data transfer rates are intentionally modest, trading speed for battery longevity. Still, the protocol's flexibility and adaptability have kept it relevant across a dizzying array of applications. Each layer in the protocol stack, each security enhancement, and each evolutionary leap in the standard has been crafted with a single goal: to make wireless connections simple, secure, and ubiquitous. As we peel back the layers of Bluetooth's architecture, we see not just a technical marvel, but a living standard, one that has grown and adapted to meet the needs of an ever-changing world. The invisible handshake between devices is the product of years of engineering, an interplay of radio science, cryptography, and protocol design. It is this intricate choreography hidden beneath the surface that allows us to take wireless convenience for granted. And as Bluetooth continues to evolve, its architecture and protocols will remain the silent enablers of our connected lives, shaping the way we interact with technology for years to come. Step into a world where invisible threads bind our devices, shaping the rhythm of daily life with a quiet, persistent hum. This is the realm of Bluetooth, a technology so seamlessly woven into our routines that, for many, it simply fades into the background. Yet, Bluetooth's full influence becomes clear the moment you reach for your wireless headphones, sync your smartwatch before a morning jog, or unlock your front door with a tap on your phone. Its reach extends beyond mere convenience, touching health, home, work, and even the way we interact with public spaces. Bluetooth's story is one of constant adaptation, subtle innovation, and profound impact on how we connect with both the world and ourselves. Consider the morning ritual. Somewhere between a steaming mug of coffee and the clatter of keys, your smartphone pairs with a portable speaker to fill the kitchen with music. Gone are the tangled cords and clunky docks of the past. Instead, Bluetooth orchestrates an invisible handshake between devices, delivering crisp audio across the room. This wireless convenience is now so expected that many forget the marvel at its heart, a standardized protocol found in nearly every smartphone, laptop, speaker, or car manufactured in recent years. The numbers are astounding. Bluetooth is the most widely deployed wireless standard on the planet, with over 5 billion products shipped each year, and projections suggest this figure will rise to 7.5 billion by 2028. Bluetooth's appeal lies in its universality and ease. At its core, the technology promises wireless connection without fuss, setup is quick, compatibility stretches across countless brands, and power consumption is low enough to keep even the tiniest devices running for days, weeks, or longer. Whether it is a mouse gliding across a desk, a game controller responding to a flick of your thumb, or a car stereo streaming a favorite playlist, Bluetooth quietly eliminates the need for cables while maintaining robust, reliable links. Its low-energy variant, Bluetooth Low Energy, or BLE, has been especially transformative, opening the door to a new generation of wearables, fitness trackers, and IoT sensors that sit power-sparingly, making always-on connectivity possible for devices smaller than a wristwatch. The revolution in wearable technology is perhaps the most visible sign of Bluetooth's daily impact. Over the last decade, the wrist has become prime real estate for innovation. Smartwatches and fitness trackers now monitor steps, track workouts, measure sleep, and even prompt us to stand or breathe. These devices do not just collect data, they share it instantaneously with smartphones and cloud services, all thanks to Bluetooth's low-power, high-compatibility connections. The market is vast and growing. By 2030, forecasts suggest nearly 250 million Bluetooth smartwatches will be shipped each year, a testament to the insatiable appetite for real-time health insights and digital self-awareness. But Bluetooth's influence in health and wellness stretches far beyond step counts and calorie tallies. The technology forms the backbone of a new paradigm in medical care, one where real-time monitoring, proactive wellness management, and seamless data sharing are not science fiction, but daily reality. Consider the array of Bluetooth-enabled medical devices now available: glucose monitors that alert diabetics to dangerous swings in blood sugar, pulse oximeters and blood pressure cuffs that beam readings directly to smartphones or electronic health records, and smart rings that quietly record sleep cycles and heart rate variability. In hospital settings, Bluetooth links patient monitors and medical equipment, streamlining asset tracking and ensuring that vital signs are transmitted directly to central nursing stations. This connectivity reduces errors, speeds up clinical workflows, and, most importantly, delivers timely information to those who need it, whether that is a nurse in the next room or a caregiver halfway around the world. The benefits for patients and providers alike are profound. Bluetooth-powered devices enable remote patient monitoring, allowing people to manage chronic conditions from home and reducing the need for frequent hospital visits. Telehealth, once a niche innovation, has flourished, with Bluetooth allowing real-time transmission of health data during virtual consultations. In elder care, Bluetooth sensors can track patient location and vital signs, alerting staff to falls or sudden changes and providing peace of mind to families. Even hearing aids have been transformed. Once simple amplifiers, modern Bluetooth-enabled hearing aids can stream calls, music, or television audio directly to the user, increasing wearing time and satisfaction while supporting emotional well-being. The advantages of Bluetooth in healthcare go beyond convenience. Low power requirements mean that medical devices can function for years on a single battery, a crucial feature for implants or wearables that must operate unobtrusively. The technology's adaptive frequency hopping helps minimize interference from other wireless systems, and government-grade security such as Advanced Encryption Standard 128 encryption protects sensitive medical data during transmission. As a result, Bluetooth has become the preferred standard for connecting everything from continuous glucose monitors and neurostimulation devices to wireless thermometers and scales. Its role in enabling real-time, accurate, and secure data sharing has made it indispensable for digital healthcare. Step outside the clinic, and Bluetooth's presence in everyday life becomes even more apparent. Picture the modern home, where smart locks, thermostats, and lighting systems can be controlled from a phone, tablet, or even a watch. Bluetooth is the glue that binds this ecosystem together. Mesh networks, supported by Bluetooth Low Energy, allow dozens or even hundreds of devices to communicate across an entire house or apartment building. The technology's low power consumption makes it ideal for battery-operated sensors and switches, while its wide compatibility ensures that new additions, be they smart bulbs, door sensors, or environmental monitors, can join the network with minimal friction. As a result, Bluetooth has helped make the vision of the smart home not just possible but practical, affordable, and scalable. In public spaces, Bluetooth's influence is growing in new and unexpected ways. A recent breakthrough, known as Auracast broadcast audio, allows audio to be shared among multiple listeners in places like airports, gyms, and theaters. Imagine a busy airport gate where travelers, each with their own Bluetooth headphones, can tune in to boarding announcements or entertainment without missing a beat. For those with hearing loss, this technology is nothing short of transformative. Auracast can stream audio directly to compatible hearing aids, enhancing accessibility and independence. Channel sounding, another recent innovation, leverages Bluetooth radio signals for precise location and distance measurement, supporting applications from industrial asset tracking to personal safety in large venues. The commercial and industrial sectors have been quick to capitalize on Bluetooth's strengths. asset tracking systems, powered by Bluetooth low-energy beacons and sensors, monitor the location and status of equipment, inventory, and even staff in real time. Smart labels and electronic shelf tags in retail environments update prices and product information automatically, cutting labor costs and improving accuracy. In factories and warehouses, Bluetooth sensors monitor machinery health and environmental conditions, feeding data to the cloud for predictive maintenance and process optimization. The technology's low-energy profile and robust mesh networking capabilities make it ideal for sprawling, sensor-rich environments where traditional wired solutions would be prohibitively complex or expensive. Yet, for all its ubiquity and convenience, Bluetooth is not without its limitations and challenges. The range of a typical Bluetooth connection, while sufficient for most personal devices, is inherently limited. Walls and other obstacles can reduce the effective distance between devices, and connections may drop or degrade if users stray too far from their phones or hubs. Data transfer rates, especially with Bluetooth low energy, are intentionally modest, a trade-off for battery longevity that works well for sensors and notifications, but is less suitable for high-bandwidth applications like video streaming. Security, while robust in recent versions, remains an area where vigilance is necessary. Risks include eavesdropping, unauthorized access, and the potential for interference in crowded wireless environments. Fortunately, manufacturers and standards bodies have responded with features like secure pairing, encrypted data channels, and user-friendly management tools, though best practices such as disabling Bluetooth when not in use and unpairing from shared devices remain important. Despite these constraints, the trajectory for Bluetooth remains sharply upward. Analysts forecast that the global market for Bluetooth modules will more than double between 2025 and 2030, driven not only by consumer electronics but by healthcare, industrial automation, and the explosive growth of the Internet of Things. Dual-mode devices that support both classic and Bluetooth low-energy Bluetooth dominate for now, but the rapid adoption of Bluetooth low-energy-only devices, especially with the rise of Bluetooth low-energy audio signals, a shift toward more specialized, energy-efficient applications. Bluetooth Low Energy to Cloud integration is enabling businesses to deploy large-scale, connected solutions from smart buildings to logistics networks, taking advantage of real-time data and automation at unprecedented scale. The future holds even more promise. By 2025, trends suggest that Auracast broadcast audio will see expanded adoption, further blurring the line between personal and shared audio experiences. Channel sounding will find new roles in safety, navigation, and precision tracking. As Bluetooth technology continues to evolve, it will almost certainly deepen its integration into daily life, supporting new forms of interaction, automation, and accessibility. The dream of seamless, invisible connectivity, once sparked by the desire to eliminate a few inconvenient wires, has blossomed into a vision where billions of devices coordinate, communicate, and collaborate in service of human needs. This is the everyday magic of Bluetooth, a silent orchestrator, connecting the dots between health, home, and the wider world. Its benefits are tangible, its impact profound, and its evolution ongoing. Whether in a hospital ward, a bustling office, a quiet living room, or out on a morning run, Bluetooth continues to shape the way we live, work, and care for ourselves and each other, one wireless connection at a time.